right, so welcome everyone to our Center for Pedestrian and Bicyclist Safety webinar titled Advancing Bicyclist Safety Through Innovative Human Factors Research, presented by Dr. Lisa Losada-Rojas from University of New Mexico and Dr. Austin Angulo from University at Buffalo. My name is Nick Frenchek. I'm the director of the Center for Pedestrian and Bicyclist Safety and a professor in the Civil Engineering Department at the University of New Mexico. Our center's US DOT-supported 5-year university transportation center. It's led out of University of New Mexico, and we've also got San Diego State, University of California, Berkeley, University of Tennessee, Knoxville, and University of Wisconsin, Milwaukee on the team. We've got a bunch of great research going on, so feel free to check out our website, pedbikesafety.org. And in addition, we've also got a webinar series, as you know. We've got a newsletter. If you go to our website, go to the bottom, you can put your email address in and sign up. And then we've also got a LinkedIn that we're always posting new papers and publications and the next webinar in our series. So you can follow us on LinkedIn as well. So throughout this presentation today, feel free to drop any comments or questions in the Q&A box. So on the bottom of your screen, you should have a ribbon. There should be a Q&A box there. Feel free to drop them in. And our program manager, Ben Garland, will be moderating the question and answer at the end of the presentation. So without further ado, let's jump into it. So we've got two awesome presenters today. I'll introduce both of them, and I think they'll kind of be handing it back and forth throughout the presentation. So first, we've got Dr. Lisa Losada-Rojas, is an assistant professor in the Gerald May Department of Civil, Construction, and Environmental Engineering at the University of New Mexico. She was previously a postdoctoral fellow at the University of Toronto St. George campus in Canada. She completed her MS and PhD in civil engineering at Purdue University. Her current research, supported by the US DOT and the New Mexico Department of Transportation, focuses on developing transportation solutions that promote community health through behavioral changes. She's currently the assistant director of the Center for Pedestrian and Bicyclist Safety and a member of the TRB Standing Committee on the Implications of Transportation Choices and Access on Public Health. And we've got Dr. Austin Angulo, is an assistant professor in the Department of Civil, Structural, and Environmental Engineering at the University at Buffalo. His research interests include connected autonomous vehicle technologies, vulnerable road user safety, micromobility, human factors in transportation, and virtual reality simulation. At UB, Dr. Angulo founded the Transportation Research and Visualization Laboratory, a state-of-the-art facility dedicated to the research, training, and education of human interaction with transportation infrastructure using naturalistic and immersive virtual simulation methodologies. Dr. Angulo received his PhD from the University of Virginia, where he founded the Omni Reality and Cognition Laboratory and was a Dwight David Eisenhower Fellow. He is a committee member of the TRB Standing Committee on Bicycle Transportation. So Lisa and Austin, thank you so much for being here, and you can take it away.
Thank you, Nick.
Thanks, Nick.
I am going to share the screen and then start the presenter. Okay, perfect. Does it look good?
Yep.
Okay, thank you so much for coming today to hear us out. So as Nick mentioned, I'm here joined by Austin Angulo from University at Buffalo. And the topic today, we will be just going through like our understanding of how we can make bicycle safety more innovative through human factors research. So a little bit about us to kind of like complement the information that Nick just gave you. And that's a QR code from my website. I'm originally from Colombia, and I did my BS in civil engineering, then went to Purdue, then to Toronto, and then I landed here a position as assistant professor at the University of New Mexico. And here I created what I call the rural and urban transportation advancements to healthier communities. When I get to work with a diverse group of people and my two wonderful colleagues, Nick and Carlos, my main interests on research are trial behavior, public health, rural transportation, human factors, and connected and autonomous vehicles. And mainly the work that I will be presenting today has been funded by the Center for Pedestrian and Bicycle Safety and the New Mexico Department of Transportation.
Cool. Yeah. My name is Austin Angulo, and just a little bit of background about myself. Here's an image of me and my students at the Transportation Research and Visualization Lab that we've just built at UB. I actually started out and got interested in pedestrian and cycling safety as a linesman in New York City. So I used to paint the lines on the roads while I was younger, and that's something my dad still does to this day. But when they were installing the city bike share program, that's when I was out there and I was watching how people use the roads, how they use different types of facilities, and how infrastructure improved safety and perception. And that kind of got me down the rabbit hole of human factors in transportation. So I've kind of made my way through my MS, PhD, and postdoc at UVA, slowly figuring out novel strategies for understanding pedestrian and cyclist safety, which has gone me down, further into naturalistic and virtual simulation methodologies. As mentioned, my research interests are really on ped bike safety, roadway design and virtual reality simulation, and integrating human factors perspectives into the development of autonomous vehicle technologies and operations.
Okay. Just to start, we wanted to hear a little bit about all the audience, and we created this QR code with a Slido. So we wanted to ask everyone, what do you think is the biggest factor affecting bicycle safety in urban environments right now? So if you want to scan that QR code, please do so and share with us. And I'll try to give you like 1 minute to try to see it live here. Um, let's see how can I do that. Okay, so I see some people participating. We work on your thoughts, perceived conflicts, speed, vehicles conflicts. Hey, speed seems to be a big factor for people. Okay, driver distraction. That sounds great. So as you keep your thoughts coming, I'll go back to the slides and then start the presentation with why we are focusing on vulnerable road users, and I pass that to Austin.
Yeah. So why vulnerable road users? Why are they important? So first, I want to start off with what are vulnerable road users. So specifically, the National Safety Council defines VRUs as anyone not protected by an outer shield. So these are pedestrians, cyclists, also potentially motorcyclists, road workers, and basically anyone that has their body exposed while on transportation infrastructure. So Lisa.
Mhm. So mainly what we see, or we are interested in this, is because of there is a huge need about safety for vulnerable road users, especially for cyclists, which is the main topic of this webinar. In 2023, there were 1,155 bicyclist deaths on US roads. In 2022, we also see 13% increase in cyclists killed from the previous year. And we also saw in 2022 that there were an estimate of 46,195 cyclists injured, accounting for 1.9 of all people injured in traffic crashes. So we believe that designing for safety requires the understanding not just of how the roads are built, but also how people think, perceive, and behave while using them. And between, I guess, like maybe this is a shared mission that we have with Austin, is trying to make things as data driven as possible, but also as human centered as possible, so we can inform behaviors, perceptions, and workloads, and create better safety outcomes when people cycle. So when we think about human factors in transportation, mainly what human factor is that science that describes the interaction between humans and systems. So human factors has been studied in transportation in a lot of the modes. And mainly how we can quantify human factors is through workload. But there are some different metrics that you will see also throughout this presentation, and you might have seen through papers or other research if you have seen it. However, we keep noticing that a lot of the focus in human factor research in transportation has been put into vehicles, mainly airplanes, trucks, passenger cars, but non-motorized modes remain under study. So to give a good example of kind of like that investment that has been done on vehicles, we have one of the first or biggest and largest naturalistic driving study, the Strategic Highway Research Program 2. And that's just a QR code to their website. So mainly this program, what tried to do was to capture different experiences while people drive in a naturalistic setting. They just mounted different devices in different vehicles across the US and capture a bunch of data from drivers. Mainly what they wanted to see from drivers was whether they were doing any improper speeding, they were distracted, or when they feel sleeping or fatigue, and also whether they use cell phones or glance at any other part of the car while driving, and also how that affected if the driver lacked certain experiences on the road, like having drive through interstates or not, things like that. So it is a big data set that it's still out there for us to explore, but again, it was mainly focused towards the drivers.
So, when we're conducting human factors research, a big thing that we want to make sure that we're doing is collecting multiple sources of data. It's been called multimodal or multi-source data sets. And taking all that through data fusion processes, we can analyze how people perceive or understand different types of scenarios, technologies, infrastructure, and operation. So the way that we kind of collect data, I like to kind of describe it in three different categories. We have sensed data, which is something that's collected directly through either different types of sensors or a simulator. So that's movement and interaction, physiological feedback, eye tracking, face recognition, anything that we can collect raw data through. That is our sensed data. And then sensed or stated data, which we call stated preference data, is collected from people directly. So that is how did they perceive their environment? We're giving them questionnaires or doing interviews so that we're getting that direct uh, perception of how they felt in a space and their own description of how that worked. Then we have observed data. So that's data that is derived from actions of people on the roads or within simulators. So that really is, what did they do when they were making a right turn? How fast were they traveling? When did they hit the brake? How did they interact with the pedestrian at a crosswalk? All of those behaviors, they're not just the raw data, but it is the extracted data from that raw data to understand decision-making processes. So I've mentioned simulation a couple times too, because this is something that's been really important within the realm of understanding both drivers, of course, and vulnerable road users. So with virtual simulation, it's actually not new in any way. I'll kind of discuss a little bit of the history in a second here, but the idea is that we can kind of study any type of technology or potential scenario or environment in a fully low risk, low cost, and very safe space. So it gives us a lot of environmental control so that we can make sure that we're not looking at compounding variables or covariation across different types of extraneous stimuli on a particular subject within a study. And it gives us different ways in which we can present information as well. So, virtual reality, mixed reality, augmented reality. There are so many different formats of displaying information and data as well, too. But really, at the end of the day, the most important thing is that it allows us to really look at detailed information that we haven't been able to understand in the past for quite a while for human in the loop testing. That is a key focus here and what Lisa was talking about before, data-driven, but then human-centric types of studies. So, as I said, I'll give a little bit of history here too. Human factors almost basically as a field kind of started almost with airplane simulation and quickly moved to driving simulation. In the top left here, we have a Volkswagen with a what we call a single screen display that was actually a motion platform that slid back and forth. But this is back in the late 70s when we were already thinking, simulation is the best way forward for understanding driving simulation. And we've invested heavily in that over the past couple of decades. That has kind of moved on to multi-screen displays, which you see in the bottom left-hand corner, multiple screens being stitched together, or something that we call a cave environment, which is in the middle top up there as well. So that's a full screen that wraps around a vehicle with images that are fully stitched together. You actually have something really similar to that in the middle bottom there, which is like more of a cave environment. But that's where someone is inside of a cave that actually moves around, so the whole thing moves as one unit. And then all the way at the far right is a simulation space in which we have a vehicle that's moving on a road or it's a simulated road, but they're wearing VR glasses, so it's fully immersive. There's no ceiling above or below you. You're fully enveloped in this space so that anywhere you're looking, you're seeing what you would perceive if you were out in the real world. So just a couple more examples here too, and I wanted to point out this in this slide here too. Here's an example of a driving simulator actually at UB, and we also have a mini sim too. But what's really important now is that in the past, a lot of these simulators were being developed on proprietary softwares, and that was a really big limiting factor. There were so many that were validated, and they've been so useful. But as we get different types of technology, especially with like the introduction of VR glasses, a lot of those technologies were not compatible. So we were getting an increase in fidelity and immersiveness, but the softwares didn't like to talk well with each other. So now, using open source platforms like Carla, Unreal, Unity, BeamNG, for just a couple of examples, we're able to integrate simulators across platforms using virtual, cave, single screen, multi-screen displays. So all of this to say is that there's been a lot of effort, especially in the driving realm, to create these simulation spaces in which we can collect really rich, valuable data. So next slide here. Because this is important because we've also been trying to figure this out from the cyclist perspective as well. It's actually really funny for cycling and pedestrian related studies. Headsets were actually developed in the very early 80s that were massive and clunky. If you can imagine playing Pong on a large screen that's strapped to your head, you basically have a TV screen strapped to your head. That was the fidelity that we had back in the 1980s for VR, but it was being developed because we knew that's where this technology needed to be to make it immersive for simulation studies. And over the years, as driving simulator technology has expanded and increased, that same technology has been able to be leveraged for cycling simulation. However, it had a lot of differences. With vehicles, you just hit a pedal and you turn a wheel, and you can use all of those sensors for immediate physical feedback. But with cycling, you're pedaling, you're turning a wheel with a physical motion and a physical interaction on the ground that is hard to translate the same way as a gaming steering wheel because you need that realistic feeling because there's a balance component to cycling as well too. So the integration of a cycling simulator is far more active than sitting in a vehicle, and that's also been a challenge as well. But as we've kind of gotten through new technological developments, that is something that is now very feasible in the realm of human factors and transportation. So what's really important here, and this image is provided to give an example of the integration of so many different types of technology for this data fusion and multi-source data being collected. What's really valuable here is that we have technologies now that translate from naturalistic environments to simulation environments. So eye tracking data, heart rate data, and understanding different types of infrastructure. We can create perfect replicas of real world environments in VR and then go through the validation process of understanding how well we're replicating something in VR and how realistic those behaviors are. And once we're validating those simulators, which we can now finally do with all of that technology, we're sitting in the same space as we have with driving simulators and their validation. They've been there have been multiple papers published in the past about driving simulator fidelity, and now that is so good that it's counted as ground truth of what we study inside of driving simulators. And we're getting to that point now too with our cycling simulators, which Lisa will also talk about a little bit in a second.
Perfect. I guess before we move into that like validation part, I just wanted to also share a couple of projects that we have done, mainly from the on-road, more naturalistic studies. And this work has been done funded by the Center for Pedestrian and Bicycle Safety, and with a couple of colleagues, Karin, Dr. Han, Nick, and a couple of the students here at UNM. So mainly what we wanted to do with this one was to evaluate demand levels in bicyclists using ECGs or heart rates and eye tracking data, and address a couple of research objectives. First, quantify physiological demands at urban intersections, and also examine if the type of intersection that the cyclist was going through had any influence on their stress. So for this study, was one of the examples that we bring today. We had 5 different types of intersections. They were of, I guess, like different control as well. So we have a couple of controlled and uncontrolled ones, with both 2 stops and 3 and 4 stop ways, and also a mini roundabout that was kind of like a different one there. So for this study, we mainly use instrumented bike, and we use the Polaris ECG, and also the neon glasses for the eye tracking. So from this study that it will be soon published at TRR, we mainly look at lateral head movement, or that visual demands, as we are going to call it, and also heart rates. And we found that when it has to do with travel direction, there were some effects that we noticed, especially for lateral head movements. When people was doing left turns, we saw a higher spike on that visual attention, or like the head movement. And also we saw that unprotected directions kind of increase that cognitive load in cyclists. And that was a very similar finding from looking at the heart rate. And again, this is not with fusing those 2 measures, but trying to look separately at each of them. And for this one, we found that head movement and heart rate offer complementary outcomes rather than competing ones. So one conclusion for this study that we can give you is that intersection design critically impact cognitive demands. And we mainly found that unsignalized intersections with unprotected directions, especially when you were going to turn left, increase that lateral head movement significant. And that heart rate also kind of can reflect that fatigue accumulation that might interact with that intersection-specific demands. And we're looking at doing some future research with integrating those multiple workload measures and controlling that physical fatigue. Another example where we have used kind of human factors research data types and methodologies for understanding cyclist safety has been in this other project funded by the center that's called Evaluating Vulnerable Road Users' Stress During Motor Vehicles Interactions. So what I'm showing there, it's a video that was taken from the eye tracker device, and we are using a YOLO algorithm to try to measure passing distance of those vehicles that are approaching the cyclist. But we also use, as part of this project, a barrier radar that, for those of you who cycle or are familiar with this, can measure the speed, the approaching speed at which the vehicles are coming. So mainly we wanted to understand if those micro interactions between cyclists and mobile vehicles have also something to do with the infrastructure, and how we are trying to do that is we are also seeing where the cyclist is actually deciding or I guess choosing to ride. So whether that's outside the bike lane, left or in the middle or right of the bike lane. And we are also seeing through the videos that there were segments that were so stressful for some of the cyclists that we have as subjects in these experiments that some of them also decided to move to the sidewalk. So we are hoping this is an ongoing project, and we are hoping to find out some of the results very soon about it. And then the last one that I wanted to offer as an example, and kind of like circling back to what Ozzy was mentioning, was understanding workload measures captures in both naturalistic and immersed virtual realities environments. And mainly the question that Austin and I kind of like, and with colleagues created in this study was which measure really validated from the simulator to the real world, because as Austin mentioned, there has been a lot of driving simulators validations, but cyclists, it's fewer studies that have done that, and mainly they haven't been able to look at a wide range of those multi-sensor data. So for this one, we mainly try to do the same route that we use in the naturalistic one. We designed that in an immersed visual environment, and we use very similar sensors to try to capture that workload from the cyclist. So from this one, we also we collected data from about 30 subjects, and mainly that data was related to heart rate, head movements, cycling speed, and we also collected some subjective data from cyclists. And we did that doing a 1.2-mile route. And we also wanted to see not only if that kind of like translation between the naturalistic and the spiritual environment will happen if we take into consideration the whole route, but also what might be about specific segments in our route. And why that was important is, well, I have always wanted to kind of try to validate that bicycle levels of traffic stress with now more human-centered data. So we were interested on that, but we were also interested about specific features of the infrastructure in these segments. That's something that you guys cannot see on the slides, but just to let you know, segment 2 has a grade. So we wanted to see if that's something, or those measures that we were taking with those sensors will be translated into our simulator, where we could then make kind of like that grade effect. And from this one, we found that mainly the measure that strongly correlate between each other was heart rate variability. We found that head movement had some limited absolute validity, so we might use it with caution, as well as cycling and some of the other subjective measures. So mainly what we found with this study was that simulators, they excel at stress and cognitive demand assessment when we look mainly at heart rate variability, but they are limited for things that might need to capture physical exception demands or any detailed biomedical analysis. So to give you biomechanical analysis, to give you an example, one thing that it was very, I guess, like not surprising to me as I am a cyclist, and I do this, of course, in an on-road all the time, was shoulder checks, right? Shoulder checks were very present when we will see the naturalistic data, but in the simulator, they were less present when we consider the different subjects that we have. And with this, I move to Austin for all the other vulnerable road user simulators.
Yeah, so kind of expanding the idea here a little bit more, and to talk about how difficult it is when we're using simulation to understand human factors. There have been a lot of developments over the years, like I was saying, especially technological dependent, that we needed to figure out in order to create an immersive space and also collect multi-source data from. So here are just a couple of examples of a bicycle simulator. There's many ways to make this more realistic, whether it be just how well your graphics are rendered inside of the environment, but then also creating things like haptic feedback. So variable speed fans for increasing the amount of air flowing and hitting the participant, whether going slower or faster. So that creates a sense of speed and movement inside of the environment. Realistic turning features, so you can actually turn the handlebars on a bicycle simulator and the bike will turn according to the same movements that you would expect while you're on the road. And then real-time speed and resistance. So if you pedal faster, the bike moves faster. If you pedal slower, it moves slower. If you're going uphill, it's harder to pedal. All of those things are very important for the types of studies that you need to do inside of those environments. When it comes to pedestrian simulation, for example, here too, that one also gets really interesting because your movement inside of a space is limited in virtual reality to the space that you're moving within, like in a room. So if you want to actually walk around realistically in a space, you're limited to the boundaries of what the room is that it provides. But as we're, developing more and more new technologies, things like these low friction platforms and different types of omnidirectional treadmills allow for more ability to move around in a space so that we can collect naturalistic moving behaviors. You can move in a fully open space, but also allow for full immersion inside of those simulators themselves. And this is an example here too. iMotions is a software that we use kind of frequently to understand what people are looking at, and this is something that's really important, and it's one of the more difficult human factors related areas to study because IDing objects that people are looking at, it can be very difficult. When we collect eye tracking data for high fidelity understanding of where people are looking, we're collecting at 200 hertz, so 200 times a second. And eye movements are very rapid. So knowing where they're looking by generating what we call areas of interest, which are these boxes over objects, can be very time intensive. As you can see in the real world example on the left side, when the person is walking here, the head is moving around a lot, and so is the person that is walking. So tracing those objects through space and time can be a very, very tedious process. So now newer technologies like automated AI, object tracking are enabling faster understanding of those types of data and quicker analysis. For example, even through my own PhD, I studied, over 200 different participants over any given period of time, and each subject for roughly 1 minute worth of data was taking me about 2 hours to analyze and draw just these boxes around for one object. So imagine tracing 5 objects in a space there too. So it's super, super important data source though, because it's highly valuable to study. So here, I'll talk about bicyclist and AV interaction. So this is a study that we've been conducting to understand how cyclists perceive automated vehicles knowingly being in a fully autonomous environment when the vehicle does something that isn't an absolute perfect behavior. So, for example, in this study, we have an autonomous vehicle approaching a T intersection. So the road that the cyclist is on with a delineated bike lane is a one-way road. This autonomous vehicle approaches that T intersection and doesn't stop right at the stop bar, but rolls past it a little bit. And what we wanted to look at was how cyclists respond to that AV behavior, knowing that they're in a fully autonomous environment. But then also look at different types of messaging that we can provide to cyclists that may alert them of the impending scenario, and then also what that vehicle's intent is. Additionally, we also add in a different format for providing that message. So we can skip to the next screen here too. Whether we can look at a phone mounted on bicyclist handlebars, and this is pretty standard now in even bike share systems where you take a bike out of the bike share station and you put your phone in it because you need to look at the map of where you're going, and it even has like a wireless charging port and things like that too. It's pretty standard. So then we thought, okay, so what if the phone app had a beep noise and said, hey, there's an AV ahead or an AV yielding ahead, so providing intent of the vehicle as it's doing something that wasn't a perfect action. And then taking that a step further, looking at heads-up display messaging on something like Google Glasses or something like that, where the message would pop up in your visual field but remain static in its position and give you that information as well. Um, this image all the way on the left too kind of describes this T-intersection interaction. After a cyclist passes a certain point, we basically have a vehicle roll up to the stop bar and roll past it a little bit. And this also lets us understand too where the cyclist is looking, how fast they're going, whether they hit the brakes, whether they move out of the bike lane into oncoming traffic from behind them. It gives us really, really valuable and rich data to look at. We're also looking at heart rate in this study as well too. So Lisa, if you click ahead here, there should be a video that hopefully is playing smoothly for everyone. But this is a cyclist biking down the road in the bike lane. You can watch where their eyes are moving throughout the whole scenario. It's giving an AV ahead message in this scenario at the top right. We have their speed being posted to them while they're traveling, and what was on the top left there was their heart rate as they were traveling down the road as well. Another example here too, so that's just talking about cyclist interaction with AV technology and special messaging for those scenarios. But here's more of a realistic scenario that could happen now, or it happens nowadays all the time. So we were doing some work with the New York City DOT here, and we realized there's no standardization for temporary work zones and the design of bicycle infrastructure around work zone facilities. And that was something of big interest to us because work zones could actually really limit someone's comfort in a situation and make them not even want to travel down a road. But it also can create conflict points. For example, here we have a moving lane or travel lane and a bicycle lane that are then being forced to into the same shared lane at a 11-foot minimum width for this design. This design is not standardized based off of any sort of data. It's just a design that the New York City DOT engineers, in fact, one of the engineers that I used to work with when I did road construction in New York City, had come up with, just because we needed something to be able to give to contractors and people out in the construction zone for designing for the facilities and the reduction of space on a roadway here. So what we did in this study here using simulation is we redesigned it. You can see on the top right there, the same scenario that was presented by the DOT. So taking a bicycle lane and a moving lane and reducing them down to an 11-foot wide lane. But then we also looked at different types of designs too, given some space requirements or removal of parking lanes and facilities in the temporary work zone to see whether or not adding more space, providing protection, etc., ended up helping out cyclists or making them feel more comfortable in their interactions with vehicles or their protection from vehicles in these scenarios. So we looked at four different ones. We looked at the shared lane scenario. Then we looked at creating a continuous bike lane by delineating it with bollards, the same scenario, but with concrete or really plastic water-filled barriers. And then looking at the introduction of an entirely new type of infrastructure technology, which is like a bicycle priority signal. You can actually see that there in the leftmost image, where there is a bicycle green light and then a full green light. So think about a road that, like a rural highway that has construction on it. They install temporary traffic signals to stop traffic from one direction or the other and allow only one flow or one directional flow in those scenarios. Here, this would operate kind of like a bike box in which it'll ask for everyone to stop, but then the bicycle light will turn green, allow bikes to go first, and then it'll turn green to allow all vehicles to move on through. So we wanted to study how cyclists perceived those environments and behaved in those spaces too. So here we also looked at different segments of the work zone itself. So the approach, which is approaching the work zone, the transition, which was at the start of the work zone, tapering into the space that is delineated or not along the length of the work zone, and then the space that was in the work zone. And here are just a couple of numbers. I know there's a lot of numbers on the screen here too, but I'll just mention real fast. We looked at multiple different models for understanding what variables were important for evaluating across all the different scenarios, how cyclists were perceiving their safety. So, for example, we have RMSSD, which is the root mean sum square of differences, uh, which is really an analysis of the RR intervals collected from our heart rate data. So those big peaks in your heart rate data, we look at the difference in time, and understanding the variability across heart rate gives us an understanding of how stressful or not stressful a scenario is. And maybe not fully intuitively, a higher variance actually means that a scenario is more comfortable. Because when you're stressed, your heart rate increases and it beats a little bit more consistently. So, for example, here, right in the middle, you can see some numbers highlighted in green and red. The priority signal actually elicited the most comfortable scenario where cyclists felt comfortable. Their RMSSD was the highest in that scenario, whereas in the shared lane scenario, where they're sharing the space with vehicles, their RMSSD is at its lowest, meaning that their heart rate is increased and that they're more stressed. And then with protected bollards and separated with like a Jersey barrier, those values are actually rather consistent with each other. So that was something that was like kind of interesting that came out of that. What was also really interesting too, in that we were looking at their lane position. A lot of cyclists ended up moving around quite frequently in the shared lane position and ended up having the greatest deviation from the edge of the work zone. So they felt like they had to essentially defend themselves and take up more space on the road, which also means that they're in a space with even 11 feet wide. It's really almost impossible to pass in a work zone. It could potentially create more conflicts, or they feel like they have to like really, really shove themselves out into the middle of the roadway to control and mitigate any potential conflicts in that segment. So here's also another really interesting study where now I'm going to talk about taking this as far as we have possibly taken it before, which is looking at multi-agent simulation. So connecting pedestrians, cyclists, drivers, and autonomous vehicles all within the same living simulation space. This is work that we've been doing with University of Michigan, their M-City facility, to understand and start developing a framework for looking at multiple agents within the same testing space, but also integrating. They're not just integrated within the same immersive simulation space, but it's a full digital twin. So we'll move on to the next slide here too, so I can describe a little bit more. So what we've done here is that M-City has a wonderful test facility, an outdoor facility where they have multiple autonomous vehicles that traverse this environment, and they've created, and now it's open source, a digital twin of that space. So it's a one-to-one replica of their testing facility. It actually has integrated infrastructure and everything inside of it, but we partnered with M-City to figure out, okay, so what if we had a driver in our simulator and a pedestrian or a cyclist in one of our simulators, and you had the AV on the ground outside moving around? Can we interact and test out real AV behaviors with simulated pedestrians and cyclists so that we don't actually have to look at the unfortunate safety critical scenarios or potential crashes that happen through naturalistic AV data, but we can rapidly test those safety critical scenarios without ever putting anyone at risk. So let's go on to the next slide here too and start this video. So you'll see that there are a couple of screens here being presented. One is a live feed at the top from M-City, in which you will see an autonomous vehicle driving through this intersection space without any other road users there. But we have in the two middle videos a driver in a driving simulator and a pedestrian in the pedestrian simulator. And on the bottommost screens, you can see the digital twin and pedestrian interacting with the AV. So the AV is actually just approached in one of these videos. It's the white vehicle there. You can actually see the same white vehicle in the bottom right video, which is our digital twin projection with the pedestrian standing in it. This pedestrian actually crosses a crosswalk, and we're just going to have them stand there for a little bit just for demonstration purposes. But then the AV moves up to the crosswalk and has to yield for the pedestrian in real life and, of course, in the digital twin because it's a live feed, and then starts moving to the intersection where it ends up reaching a conflict with a stalled vehicle in the middle of the road. It has to yield for that vehicle. You can see it in the bottom two videos, the virtual projections of it, and the topmost video, just the AV actually interacting there. And then once that vehicle clears, the AV progresses through its movement. So that is just a demonstration of what and where all of this technology is going. Because if we can leverage human factors related data sources like eye tracking, stress, and everything else, we can start to incorporate that data into the rapid development of autonomous vehicle technologies or operational behaviors across various operational design domains, but then also understand how we can, or what data sources make the most sense for us to mitigate safety critical scenarios so we can figure out, okay, now not only what does the vehicle need to do, but how does it potentially respond to or interact with someone out on the road when there is no driver to let them know it's safe to cross, or I haven't noticed you potentially. So that's really, really important data sources here for us to understand.
And I think with that example, we just also wanted to kind of like at last hear from you about which emerging areas excite you the most for advancing bicycle safety research. So you're invited again to scan the QR code and let us know your thoughts about this. But it was a pleasure for me to share this stage with Austin. There is so much that I learn from him every time I talk to him, and this is everything that we have for today. So we will open to questions.
All right. Great presentation. That was really interesting. We do have a few questions in the Q&A. So the first one is, they asked specifically about slide number 17. It said, wondering if you looked at different vehicles, for example, a car or SUV or pickup truck interacting with the bicyclists in terms of the visibility or hard braking for left turn movements.
Oh, we did. We actually did not for this study, and we are doing that for the subsequent study, the evaluating vulnerable road users stress. So things that I missed to mention there is that we are also capturing like vehicle size. I was also interested in vehicle color as well. I thought that that could be an interesting variable that we will look at. But for the previous study, we didn't consider any of the micro interactions. We are doing that right now, currently as part of one of the funded projects for the center.
Great. Next question. Have you been able to implement realistic turning without causing simulator sickness?
Yes, we have. That is a very hard thing to actually get to. One of the most important components, honestly, of that, in my experience, is the frame rate of the technology. There is, you're sitting on a bike and you're expecting to be able to turn by leaning. There's a gyroscopic motion inherent in bike riding that is just not translated over to bicycle simulator. One of the most important things is in developing these simulations, creating very realistic environments with a sense of depth and space using shadows, highly realistic textures. That helps a lot in understanding. But when turning, a big component is the frame rate of the environment itself. So how many frames per second can that space generate for smooth movement? That is the biggest limiting factor and creator of simulation sickness when you're trying to mitigate for the fact that you don't have inner ear movement actually happening. So once you start breaking the threshold of around 90 hertz, so 90 frames per second of frame generation in a space, that ends up creating a more realistic space and drastically decreases simulation sickness, especially for turning with cyclists.
All right. Next question is, are your volunteers actual cyclists who have experienced many different situations? Because they say someone who rides daily may show no physical stress response to a situation that would terrify a beginner. And then also the related question is, have your studies included fatigued cyclists who have been riding for an hour or longer?
I guess like we can take turns on that one. I feel like from the UNN side, I guess like the biggest constraint has been passing the institutional review board, right? So of course they don't want us to take someone who has never been on a bike and get him do or she do these rides in mixed traffic, right? So mainly we have been collecting this data from people who cycles or at least feel comfortable cycling. And as part of the data collection that we do, we also ask transportation habits. And in general, the people that we have had as part of these studies are not like commuter cyclists. Most of the time they drive to work, but they feel comfortable using a bike, which is kind of the main constraint that IRB give us when we are recruiting participants. And I think regarding the fatigue, at least for the naturalistic studies and the VR versus naturalistic that we did, we also ask people before they get into the bike whether they have done physical activity before, and also whether they have taken caffeine and other things that might create, you know, a highest heart rate than usual, but also to try to control for those like individual fitness levels. I would call them like that. We usually take base rate or base heart rate that we compare against what they experience while they ride the bike to try to control a little bit for those whose heart rate might be different because of just individual differences that we have as human, right? And I think that's also kind of the beauty of working with this data. A lot of things really surprise you, but it has been very interesting to see how the human body reacts to a stimulus that they see when they ride a bike, and especially the bike in the naturalistic environment being such a like active thing, right? Because you are pedaling, you are also moving your head, you are scanning your environment. So how we are able to kind of adjust the measures that we take for all those different potential co-founders of the data. But I'll let Austin respond from more his experience at Buffalo.
Well, I'll just kind of echo what you said, Lisa. We look at both types of users and actually just control for that in our analyses, whether that be using like different mixed models to understand just like variations in environment type and infrastructure type on outcomes. That is a control that we have. So, you know, highly experienced versus not experienced, and looking at whether or not those groups are different or the same. Typically, what's actually the most interesting is that their stress levels tend to be, at least in my past experience, kind of the same. Their behaviors tend to be very different. The experienced cyclists tend to not actually obey the infrastructure as much and be far more aggressive on the roads with taking up space, solely because they have an understanding of what might end up happening on the road itself, and they've been in enough scenarios to understand I need to potentially be aggressive in this scenario to protect myself. So the stress metrics actually end up being somewhat similar. The eye tracking metrics, not so much. The experienced cyclists actually focus on the bike lane a whole lot more than non-experienced cyclists, like when we have different types of protected enclosed facilities, because they're looking, at least after in like post-study interviews and follow-up questions, they're looking for debris on the road, glass on the road that maybe someone that's not as experienced might not be thinking about, you know, pop tire in the middle of a trip. So some things do differ across the groups, and they are controlled for in our studies.
All right. The next question is, are you controlling for e-bike versus conventional bike in the studies? In particular, because car drivers will use basically try to predict bicyclist behavior based on whether they're pedaling or not. But if they're using an e-bike with throttle assist, they might not have that kind of feedback.
Yeah, actually in ours, no. Mainly what we have been using is just like not e-bikes. But I was actually in conversations last week with PNM, which is like the energy provider in New Mexico, and they are very interested about replicating some of our studies. with electric bikes and seeing differences. But it's not something that I have yet explored, but something that as you know, we hear interest from people, we look forward to do. And I don't know, Austin, if you have ever worked with electric bikes before.
We've done some situations in which we're trying to control for like e-bike or classic bike or like conventional bike in types of changing the speed or how easy it is to travel at speeds in the simulations, but those don't look into body tracking or vehicle behavior around those movements themselves. That would need to focus more on a driver related study around the cyclist behavior, which I haven't done in the past.
All right, next question. Can you speak to the ways in which human factors research can be implemented to improve bicyclist safety? And do you see this research impacting design standards?
Yeah.
I think
Please.
I think I mentioned that briefly. Like one of the, I guess, like the motivators for me to get into this area of research was also trying to validate some of the methodologies that we have put out there that are mainly cars centric. Like an example could be the bicycle levels of stress, right? That we measure all of this stress mainly from like a stress to the bicyclist, but mainly looking at the speed of the cars or the space that is given to the cars. Well, also the space that is given to the bikes, but does it translate to actually what the cyclist feels? It's something that I'm looking forward to discover as we progress with this work, and hopefully it does, and we get to just use kind of secondary data to estimate stress in cyclists, but the idea will be that if it doesn't, then that help us to modify those methodologies and in translation, modify how we are designing infrastructure, bicycle infrastructure across our cities and also, of course, rural areas as well. But Austin.
Yeah, I'll try to answer this question and another one that's was actually posed here about the standardization of bike facilities. Someone commented about FDOT standard plans and stuff. So standardization of infrastructure design, I'll use the construction environment as an example. Designs have been created and standardized. They're in books and plans, but they don't have any naturalistic data or any human-centric data to back the standardization itself. We know, okay, like this is what we need to do in order to keep the lane width throughout a facility, but we actually don't understand what is the most comfortable for a cyclist in that given scenario. So when we're looking at all of this human-centric data through either simulation or naturalistic studies, that gives us a much better understanding of what works and what doesn't. To go a little bit deeper in the study that I was presenting for construction zones, RMSSD, so the heart rate variability, was found to be not different across the bollards and the barriers. But when we were looking at eye tracking data as well, the bollard situation ended up exhibiting higher indication of stress in cyclists' visual workload because the bollards are passing. So it causes a lot of distractions and their what we call gaze transition entropy, where they look and how fast they move in between different objects or how frequently and randomly they do that, was much higher than it was with the standard Jersey barrier type design. So that type of information does give us a lot of information in terms of like, well, if we put out bollards, that might actually cause a lot of stress still in the cyclists compared to the barriers, or how wide the lanes might need to be, or the spacing of the bollards. That spacing might need to increase because of weird visual like and peripheral vision distractions for a cyclist. So what that could correlate with, for example, is a lot of visual side distraction means that a cyclist could be moving or could veer more towards the direction in which their distraction is, and end up getting closer to the bollards and potentially cause a dangerous situation into like running into them. Or, if a car were to breach into it, it could be more of a safety critical scenario. This is just more of a loose interpretation here, kind of spitballing on the idea, but that's why a lot of that information is very valuable.
Great. Well, that's all the question. Sorry, that's all the time we have for the Q&A. So, if you want to remind everybody how they can contact you if they have further questions, and say any final words, and then we'll let Nick close us out.
Yeah, I think our information is there, both our emails and websites for the labs, and of course through the center. Yeah, if anyone has any questions, follow-up questions that they will want to reach to us, this is the information.
Yeah, definitely. There were plenty of other questions down there that we didn't get to, but if you do want to still ask them to us, please do. I saw some great questions in there.
I am not able to see the questions because I am sharing this screen.
Yeah.
But thank you so much, Nick, for having us here.
Yes, thank you.
Yep. Yeah. Thanks, Lisa and Austin. Great work. And thanks, Ben, for leading this. And then, yeah, thanks everybody for participating. Again, feel free to check out our Center for Pedestrian and Bicyclist Safety website, sign up for the newsletter, tune into future webinars, and follow us on LinkedIn. And we do have another webinar scheduled for June already, safety cities. So kind of miniature road environments for educating kids on how to safely interact out on the streets. So that's coming up, I think, June 24th. So please check it out. Yeah, thanks again, everybody, and see you next time.
Thanks again.
Thank you.